All right, good morning. This video is to help you construct a spreadsheet uh, for an RLC circuit, so a series RLC circuit. I started out already here. Uh, Good thing is a description, what is the code going to do? So this says here, we're going to take inputs for the RLC circuit, and those inputs are these 5 quantities here. Your EMF amplitude, the frequency of the EMF. So those are like two of the EMF qualities. Then inductor, capacitor, resistor. With those 5 things, this code is going to calculate reactances, the resonant frequency, the voltage amplitudes, the phases, which really there's the main thing is the phase between the current and the EMF. And then the time dependencies will actually plot all the sine waves. So we can kind of take a look at that. And so you can use this problem and the homework, which the homework's already due, so that's too late. But there's these 2 problems in the homework you could use this code for. Also, I'm going to ask you to do 3229 and 3230 to use this code to do those problems. It should just take a couple minutes after you've got the code working. So here are our inputs, EMF, frequency, RLC. It's good to have a description for each thing. I'll leave that for you to put some of those in. The units, good to know what units you're working in, and then the numerical values. So those are the inputs. Let's look at the outputs here. Okay. So the outputs 1 omega. So we're given a driving frequency, but we need the angular frequency. And so I'm going to use W, even though it's actually omega. And then there's omega naught, which would be the resonant angular frequency. And then F naught, because it's good to also have your resonant frequency. So you have the resonant angular frequency and then the resonant frequency. The angular frequencies are in radians per second. And the regular frequency is in hertz, or just inverse seconds. All right. So let's compute these. The omega is simply you take the frequency and multiply by 2 pi. Let me try that again. 2 pi times the frequency. Okay, so right now I have the frequency at 1 megahertz, and then let's start it out a little slower though. These values, the nice thing about what we're going to do here is these inputs you can change to whatever you want. And so I'm just made it the driving frequency 100 hertz. And so at 100 hertz, we have 628 radians per second. Now the resonant angular frequency, that's this formula 1 divided by the square root of L times C. So L times C. And those, I just have some kind of starter values in there, 1 millihenry and 1 microfarad. So if we did do that though, our resonant frequency is going to be 3.16 times 10 to the 4, or like 31 kilohertz. That would be our resonant angular frequency. And then our resonant frequency is just the angular frequency, and then divide out the 2 pi. Okay. All right. So around 5,000 hertz, that's going to be the resonance. All right. So the next few things we can compute would be reactances. So the inductive reactance XL, the capacitive reactance XC, and then once we have those, we can compute the voltage amplitudes. Well, actually, I think before that, the current amplitude. We need the current amplitude I naught, and we'll have the voltage amplitude over the resistor, voltage amplitude over the inductor, voltage amplitude over the capacitor, and then the phase, phi. This phi here, this is the amount the current lags the EMF. So if it's negative, then that means the EMF lags the current. But that's going to be, we'll do that in radians, not radians per second. Excel's trying to finish my formula for me. Okay. All right, and you know, I like making the font a little smaller here, so I'm just going to select those. I'm going to go to font and make that like 10. So maybe 8. So that way it can fit on there. All right. The reactances, these are all in ohms. So even the inductor and the capacitor have ohms. And all the voltage amplitudes are in volts. Okay. All right, so now we got to calculate each one of these. XL is omega times L. Omega times L. All right. XC is going to be 1 divided by omega times C. And so I'm not using the resonant frequency there. I'm just using the given frequency. That's whatever the EMF is running at. And so notice here we can see the circuit already working here. So my XL is 0.6, right? 0.6 ohms. Whereas my XC is 1,600 ohms. So XC is huge. Why is XC so big? Our frequency is only 100 hertz, whereas the resonance is 5,000. So we're way below resonance. That puts us in a capacitive regime. If we were to go way above resonance, so let's try here, I got 100. If I go to 10,000, now I'm way above resonance. And we see this, the numbers, the actual digits stay the same, but if you look here, we have the XL is now 60, 63, and the XC is only 16. So now we're in the inductive regime where we're going faster than the resonance. So I'll go back to 100 just to, so okay, now it's still at 100. So, all right. OZ, let's look at the impedance. So I need to add, whoops. I want to add here another column. So I'm just going to, actually, there's a couple ways I can do this. I cut this and I pasted it in. You could also just add a row there. But I need to put in my Z, which is the impedance. It's kind of an intermediate thing. So the impedance, that's like this generalized resistance. It's the square root of R squared plus the difference between XL and XC. So XL minus XC squared. So that's our impedance. And it's around 1600. So basically it's the same as the capacitor. At this slow frequency, the capacitor is creating most of the impedance. Okay, and then I naught, it's pretty simple. It's just the driving EMF value, the amplitude, divided by the impedance. All right, so we're getting 6 milliamps out of this thing. Now these voltage amplitudes are pretty easy to calculate. They're just the reactance times the current. And the reactance for the resistor is easy because it's just a resistance. So we'll do the current times the resistance. That'll give us the resistor voltage amplitude. And I should probably put that in here, the resistor. Even with my small font though. Actually, that's not so bad. So let's go in here and just make this clear. Each component has its own voltage amplitude. All right. Now I'm just going to continue on with these, computing these amplitudes. Each amplitude is easy. I naught times the reactance. So we're doing the inductor here, so I'm going to use the inductive reactance. Very small voltage over the inductor. The capacitor, I naught times the capacitive reactance. And then I'm getting 9.98. Why is that almost 10? Well, if we look, the EMF amplitude itself is 10. And so when you're in the capacitive regime, you basically, we're in the extreme capacitive regime, almost all the voltage is across the capacitor. All right, and then the phi. The phi is going to be an inverse tangent, so that's A tan. In Excel, that's how Excel takes an inverse tangent. So A tan, then we'll do XL minus XC divided by the resistance. Okay. That looks good. So now we're at a negative 1.5. And you might notice negative 1.5, that's basically negative pi over 2. So this actually means since phi is the amount the current lags the EMF, now the current is leading the EMF by about almost 90 degrees. And that's also a capacitor kind of thing. All right. So that's it. You can now do, I think, some of these problems. Maybe most of these problems you can do right here. All you need to do is change the values of the inputs, and it should recalculate any of these quantities you need. Current amplitude. Okay. So the next thing we want to do is do the time dependence. I want to actually see these sine waves. So now I want to make like a little time vector so I can plot some stuff. So first thing is, how many points do I want? So I'll say n, this will be the number of points. And so let's say I want to have 200 points. Okay, then my plot, my x, the time vector will have 200 different points. But now I want to think, how do I divide that up so I can get what I want to see? I want to see around 2 cycles. So I'll just say the number of cycles. The number of cycles here, I'll give myself 2. So we're going to have 2 cycles. And we need the period of each cycle. How long is each cycle? So I'll just do say t there. This is the period. And this is the seconds. The numbers don't have any units. So, oops, I just wanted to be a minus sign. There. Yes, the numbers are unitless. But the period, what's the period? 1 over the frequency. So we're given this input frequency right now, 100 hertz. Okay, so you got 10 milliseconds. That's the period. And so dt is going to be our little time increment. That's also in seconds. And so now what I want to do is I want to make dt 1/200th of the total amount of time I want to cover. The total amount of time is 2 periods. So I'm going to say equals 2, or the number of cycles, so I can change that if I want to, times the duration of 1 period. So now that's going to be 2 periods of time. I'm going to divide that, divide that by the number of points. Zoom in there a little bit, that was weird. Oops. Maybe I should zoom out. Oh, can't show my whole screen at once. All right, so there's my time increment, 1/10 of a millisecond. So that times 200 is going to give me 2 cycles. All right, so that's my dt. So now I'm going to come back up here and make a little sequence of vectors to plot. So we have our time. What else are we? There's voltages over each component. So we have the voltage across the resistor as a function of time. we have the voltage across the capacitor as a function of time, voltage across the inductor as a function of time. And you know what? The EMF I'm going to insert here. So I forgot the EMF, so I'm going to click right there and do insert, and it's going to know to put a column in. So I'll do my EMF here. That's going to be my EMF. My big E is EMF here. Okay, so we have these four components, and I want to see their voltages as a function of time. So let's look at the time first. We'll start at 0. It's a very small font. I guess somehow it's related to my changing those other fonts. All right, so start out with 0. What's your next point? I'm going to take the previous point plus dt. So come down there. And I'm going to have to money sign that dt so it doesn't change when I drag. All right, so now I've got that, and now I just want to implement the other these other equations. So EMF, that's defined a certain way. We define it to be, man, this font thing really. I just do this, so I select them all, and I just want, please be 12. Oh, looks like it worked. Okay, so I want to do my voltage amplitude times cosine omega t. So you got your omega, and then the t, that's gonna be the variable. Everything else needs to be money signed. So if it's not in column H, it's gonna be money signed. Well, basically anything D, anything in column D is gonna have to be money signed. Right. So that's our EMF. Starts at 10 volts. That sounds good. Now the resistor. Resistor amplitude times, let's see here. This is going to be a cosine. Now, where is the phase of the resistor? Turns out the resistor is in phase with the current. So I can use that phase to find out the current. I'll do my omega times the time. And then what I'm going to do is subtract the phase. So what am I subtracting? This phi here, the amount the current lags the EMF. And so I'm going to click there. And so now if we go to the very top, here's my equation for the resistor voltage. So the resistor voltage is going to be in phase with the current. And so I'm just, this phase here that I'm putting inside the cosine, that's the same as I would for the current. I'm not actually going to graph the current because I just want to graph voltages. Money sign everything in the D column. All right. So that's our resistor voltage. And here we're subtracting, so that means we're lagging by D23. D23 is this phase, which is negative pi over 2. So that actually means we're leading. The current is leading the EMF by around 90 degrees. So hopefully we can see that when we plot them. Then we have the other two. The capacitor and the inductor, we know their phases. So let's look here. Resistor phase is in phase with current. So you're using here for the resistor, we'll say a cosine omega t minus phi. That's what I'm putting in for the resistor. And the capacitor, I'll say the capacitor is going to lag 90 degrees from the current. And the inductor leads current by 90 degrees. So it's all based around the current. You find the current from the phase phi. Once you've got that, then you can just space your capacitor and your inductor by lagging or leading 90 degrees. All right, so the capacitor voltage, we use the capacitor voltage amplitude times cosine omega times t. Then we have to subtract up the phase like before. And now I have to actually lag even more. So I have to do minus pi, and pi has this parentheses here in Excel. So minus pi over 2. There we go. And now I'm going to input the money signs. Hopefully that's right. Okay, 9.96. So we're starting out with almost all the voltage. Not quite 10, but that's just I guess it's not quite 100% capacitor. Now the inductor should be very similar, except we'll lead by 90 degrees, lead the current. We'll do the voltage amplitude times cosine omega times t, then minus the phase. And then we're going to add pi over 2. And then I'm going to unassign these, and then hopefully we'll be done. And there. All right. So let me drag this time vector down to 200 units or so. All right. So it looks like it's getting bigger and bigger. All right. Now I'm going to highlight all 4 of these and just double click right in the corner once I get the black plus sign. Double click and boom. All right, so it should have a lot of interesting stuff here. Let's graph the EMF. So I'm going to just select these 2, insert. Usually I like scatter plot because I like to see the points, but this is a smooth curve. We might be nicer to have some lines. So I'm just going to pick a line. All right, so there's a weird point at the beginning. So I'm actually going to see if I can, there we go. All right, so that's getting gone. And this is kind of ugly with all those. I don't know why that's like that. So what I'm going to do is do format axis. And it's like the labels. So down here in the labels, I've done this before. I don't truly understand how it works. But if I specify the interval number, my goodness, and if I make it bigger, so this is what I've found out. So like, I don't know what that 60 represents, but somehow it makes it a little nicer. Maybe 100, I'm not sure. Maybe if I do 100, then there'd be only one label on the whole thing. Yes, so I think 100 is like a percentage, I guess. If I do like 40%. Okay. All right, so, well, we've got our 2 cycles. We got 1 cycle, 2 cycles. So that's what we counted on. And this is the driving EMF. So what I'm going to do is go to select data. So this blank series, I'm going to name it. I'm going to call this the EMF. All right, oops. I didn't want to leave there. I'm going to go back to select data. Select data is my favorite place. Okay, so now I want to add another legend. I want to add another series. So I'm going to do a plus sign here. And I got to grab these Y values. So I'm just going to click on that box to create a chart. Let's see, let's claim 1 value. Yeah, okay. So what I'm going to do is grab this and just go all the way down. Okay, so press enter, that inputs those there. And the horizontal axis, I got to plot the X, the time. This isn't the easiest way to do it, but I was having a little trouble doing it all at once, so I decided I'd do it like this. So this is the voltage across the resistor, which is in phase with the current. All right, so let's see what we got here. All right, so this is very small resistor voltage. Okay. But what we see here, what do we see? The resistor is actually leading the EMF. Actually, let's get a legend on here. So I'm going to, I want to insert a legend. So what I'm going to do is go to chart design. Over here on the upper left, there's add chart element. And so here there should be legend. There we go, legend. Okay, so here's my legend. EMF is the blue. The resistor voltage is orange. All right. All right. And these don't really need to be in scientific notation. That's a little ridiculous. So I'm going to see if I can actually. So if I click, notice I've highlighted this y-axis, and then on the right format axis, if that's closed, you can always just click on it, right click, and then where'd that go? Format chart area, I think would be it. And so then once it opens up this pane, it deselected my thing. So I'm going to go back, and these 3 blocks right there, that's the one. And so I can set my axis options. Let's see here. Number. I don't like the scientific notation. So I'm going to, the categories on scientific, I'm just going to put it on number. And we don't need any decimal points there. Okay, so, and those should probably be labeled. I would definitely label all these. All right, so let's see what happens. So our resonance is supposed to be, and let me highlight this little box there. This is our resonant frequency, 5,000 kilohertz. So let's see what happens as we go to 5,000 kilohertz. I'm at 100 hertz. So let's say I go to 1,000 hertz. What's going to happen? Okay, so I went to 1,000 hertz. My resistor voltage got a lot bigger. The resistor voltage is still leading the EMF, and it's not as big. But let's see what happens as I approach these 5,000. So I go to 2,000. That's what I love about these recalculating. Okay, 2,000. You can see this phase is getting smaller, and the resistor is getting bigger. That's what happens when we approach resonance. So 3,000. Now we're almost there. So this is a wide resonance. Let's try here, 4,000. Not quite. And then 5,000, it looks like it's 5,030. So nail on the head, boom. So now they're like the exact same. You can't even tell them apart. So that was a wide resonance. You notice it was even at 3,000, which is like really far away, it's still like almost resonant. So you can actually make that narrower by playing with the resistance. Oops, there's data already here. Okay. So what I'll do here, I'm at 100 ohms. Let's say I just go to 1 ohm. How does that look? So boom, 1 ohm. Now it's gone all of a sudden. I'm at 3,000 and it's tiny. However, the resonance is still 5,000. And so let's see what happens as I go closer. Now I got 4,000. Yeah, it's picking up a little bit, but let's go. I got 4,000. Let's go 4,800. There we go. But notice this is what I would call a much more narrow resonance. You got to get all the way to even at, let's see here, 4,000. Let's go 5,000. There we go. At 5,000, we're almost there. And then 5,030. Oops. 5,030. Boom. Then we're hit the nail on the head again. So that your resistance changes a lot there. Okay, so that's kind of a resonance. Well, let's look what happens when we go past resonance. So now we're at 5,030. What happens if I go to 5,000, 100? We'll go up above resonance. So, okay, so now we see the opposite thing happening. Before the resistor was leading the EMF, now the EMF is leading the resistor. So that's the other side of the resonance. And so we go 5,200. And we're leading by more and more. We can go to 5,500. And notice right where the blue line crosses 0, that's 90 degrees from the top, right? And that's right where the blue line crosses 0 is almost where the resistor peaks at its maximum. That's the 90 degrees phase. That's, well, it's not there yet, 1.39. If we're gonna, we could convert this into degrees here. I could take the radians. How do I convert to degrees? Multiply by 180 divided by pi. So we're at like 80 degrees. So it's not quite 90 degrees. If I keep going up, I'm at 550. If I go all the way to 6,000 hertz, then it's hard to see, but I'm at 85 degrees and maybe 7,000 hertz. Getting tiny, but now we're 87 degrees. So you can see how it's limiting. It'll limit, so we're now in the inductive regime. It'll limit to being lagging. The current is actually going to be lagging the voltage by 90 degrees when we're in the inductive regime. Capacitive regime, it's the opposite. The other things I'd like to plot here are the capacitor and inductor voltages. So I'm going to do select data and add those two as well. So I'm going to do a plus here. Wish I could just copy one so I don't have to do the x-axis again. Let's try. Okay, so VC. Okay, enter. And actually, I could be a little smart. I have been really not smart about this. Let's see, VC. One thing I could do is, oops. I like pressing enter, but then it gets me out of select data every time I press enter. So let's see, VC. What I'm going to do is take the X data from VR, because it's the same X data, and just paste it into the VC. And I'll make another guy here. And I'll use that same X data there. And I'll call this VL. Whereas, did I get the C and L mixed up? No, I did C first, then L. All right. And I'm actually going to take this stuff. This is the K. Notice it's a K column kind of thing. And I'm going to switch it from K. What's after K? L. So I'm just going to swap out those little L's so I don't have to. Okay. All right, so now we have all four of them going. So it starts looking crazy. But let's see here. Oops, there's not, why aren't they all, they're not all in the legend. So let me see. Well, why isn't the VL in the legend? Maybe it is, and I just didn't notice it. Where'd it go? I think maybe I have to expand this. There it is. All right, so how does this all work? One thing is the gray and the yellow, the VC and VL. Notice they're 180 degrees out of phase. Where the gray peaks, the yellow is the most negative, and their cross is 0. They're always going to be that way. That's that phasor diagram where VL points one way and VC points the other. That's the 180 degrees. And we are in the inductive regime here because I'm way above resonance. I'm at 7,000. And that's why the blue and the yellow are phased up. That's inductive regime. Let's move down to 6,000. What's going to happen? We'll move back down here. Notice the inductor is getting even bigger. This is what's really weird to me about the circuit is look at the blue curve. The blue curve is maximum 10 volts. That's the driving EMF. That's the thing that's bringing energy to the circuit. However, even though that's the thing driving everything, both the capacitor and inductor have a larger voltage. If you go around the loop, they cancel each other out because they're out of phase, but they do have these huge voltages. So that's fascinating to me. Let's go down to 5,200. And so now just look how big those inductor and capacitor voltages are. They're just massive. And actually, we can make those a little smaller. One way is I've got this well, actually, I'll just continue down. Let me go to resonance. So let's go right on resonance, and then boop. This is resonance. Look at this, 300 volts. My capacitor and inductor are going up to, but they're adding to 0 because they're like exactly opposite. So that's funny. Those voltages don't have to always be that big. That has to do with the tiny resistance that's happening. So if I make my resistor bigger, that's going to reduce the current. And note, let's see here. I go all the way to 100. Yeah, see, if I go to 100, now it's inverted. The inductor and the capacitor are smaller, and the resistor and the EMF have a bigger voltage. So it's not that always the inductor and capacitor have a big voltage, but depending on the resistance, they can. Let's go below resonance and see what happens, 4,900. Not much. Oh, now I guess now that I have a big resistance again, it's a wide resonance. So let's go down to 4,000. Okay, we're starting to leave resonance a little bit. Let's go down to 2,000. What's happening here? So the red curve or the orange curve is the resistor. So the resistor is starting to lead the EMF. And the capacitor is the other one I want to notice. VC. Let's see here. We should be converging on a capacitor. Let's keep going. I want to go to 1,000. There we go. We can see the capacitor is starting to converge on the blue curve. The gray and the blue are becoming the same as we're in the capacitive regime. So the inductor, which is the yellow curve, has no voltage over it, has too high of reactance. The inductive reactance is too small inductive reactance. Let's go all the way down to 500 hertz. And there we see the resistor voltage is just kind of out of phase. The inductor voltage is gone, and the EMF and the capacitor are converging. If I go all the way down to 100 hertz, which is where we started, then boom, we just get basically the capacitor is the only thing with voltage across it at that point. All right, so you can use this code to do those problems. And I would also like to see some different regimes and phase relations between those different curves. All right, thank you for your time.